example on the moment distribution and give you an overall summary of the course. So the last example will be on the frame structure with translation. So previously we discussed the moment distributions, and all the examples that I show you do not involve translation, and distributions were carried out at a joint, assuming that the degrees of freedoms involve only rotational angle. But a lot of cases happens that the structures start to have translation. So very simple example like this. So can the moment distribution method address this issue? So if I put a hinge support here, if I put a hinge support there, then the analysis, moment distribution analysis become very straightforward. So what you need to do is to convert that to the joint using a fixed end moment concept, and then you can start to carry over all balance and distributes, and then you just follow through the loop. Then you will be able to calculate and obtain the solutions because it only involves the distributions which is directly related to the angle at the joint, so nothing else. But if there's no hinge, then you know that the structure is going to be deforming like this. So that will be the deformation shape. And in addition to the rotation angles, we also have this translation of the beam, which is again unknown, just like a rotation angle, but the whole approach of moment distributions develops assuming that we know there's a rotation angle, but we don't care how much it is, and we just want to find out the forces. So we skip the calculations of rotation angles, directly go for the force. So right, that's why we have a distribution factor coming in. But with this additions there, delta is another unknown. So you won't be able to directly use the moment distributions to calculate because it involves rotation angle as well as translation. And this translation is unknown. If it's known, then we have ways to do it, just like settlements, right? Previously, we have a settlement issues, so we use the fixed end moment concepts to take care of the settlements. So if this is given, then we can still go for the mass moment distributions. So that's where the creativity comes in, and the superposition concept comes in. So you need to decompose the conditions into two conditions where you can operate. So this is what you can do. First, you assume that the structure has a hinge. So here's a P force. You assume that there's a hinge or roller, make it simple. So you can do a moment distributions on this, no problem. So you can do moment distributions. And eventually, you are going to get all the forces out, internally, externally. And you will be also able to get this force out reaction force. So let's say reaction force is R. So after the moment distribution, you should be able to get all the forces, including the reaction force, out. And then you use the concept of superpositions. So you say that the force is there is because you assume the roller conditions, so you can compensate that by applying a counterbalance force, R, there. So you can see that if I add this case with that case, then there's no R, there's no support. They'll go back to the original conditions. OK, but still, we cannot solve this issue because once you have the loading like that, then you have translations. So it's the same as that. We didn't resolve the issue. We did not resolve the issues. However, we can do it this way. People are very, very smart. So this is what we can do to overcome this. So we assume that I have a translations. Let's say 1 centimeter, 2 centimeter, you just assume a value there. And then you calculate how much is the force that required to generate such a displacement. So instead of applying loading, calculate deformations, which you cannot do using moment distributions. You assume that I have a displacement, and then back calculate how much force is required. That we can do using moment distributions. So you can do a moment distribution calculations, assuming you have a deflections, and then calculate how much force is required. So after you've done that, then this result and that results comparison. So now you have this value. You have that value from the first calculations. So you just take all the values here, multiply by coefficients of R over Q. You take everything here, multiply by R over Q. Then you have this case. And this case superimposed with that case, then you have the solution. All right, so as a result, if you want to use the moment distributions to calculate this kind of problems, it will involve two separate moment distribution calculations. Right? First, you assume it's roller support, no translations, and then calculate the reaction force, back apply the reaction force, but through the assumed displacements, back calculate how much the force is required, and then scale it back. So that's ways to address the issues of translations. So I'm going to illustrate this concept using the last example here. So we have seen this example before, solved by a different approach. All right. So follow the same concept. I know that this structure under such a loading is going to have a sway or translation because the structure is unsymmetrical and loading is not symmetrical, so it's got to have some sort of translation. So I do the first analysis involving putting a roller support here. this is fairly easy to do. So I name this A, B, C, D. So I need to calculate distribution factors here and there. So please verify yourself. I have two sets of distribution factor, CA and CD. They are the same, 0.5. Distribution factor at D, DC, is 0.42, and dB is 0.58. All right, fixed end moment. So I go to the table to look this up. So what happens for the end moments if I have a loading applied at this positions? Right. So I go to the fixed end moment table. So as I remind you that in the final exam, you are required to memorize UDL, fixed end moment due to UDL, and fixed end moment due to concentrate load at the mid-span. If for problems like this, I will supply you with the fixed end moment equations. All right? Clear? All right, so you should have fixed end moment. And the fixed end moment is 39.18, and this is 29.39. All right, so then you can directly set up to calculate the moment distributions. So this is A, C, D, and B. First is distribution factor. And start from fixed end moment. So this is at the span of CD. So it's right here, 39.18. And this is 29.39, but it's clockwise, so it should be negative. So that's the starting point. And you need to remind yourself, these two are coming from the climb assumptions. So immediately you need to do a balance and distribute. So you balance that by negative and distribute. Followed by carry over. So you look around from here to here, carry over. And from here to here, carry over. And in between, you need to carry over as well. So carry over. All right. So which ones are assumed? This is not assumed. This is assumed. So then you do balance and distribute on this. Carry over, balance, distribute, carry over. So you should have a few more steps to complete. All right, so finally, you need to do a summations. So please verify yourself. All right, so that's the calculations I got from the first moment distributions. So this is where we are. Now I need to go into the component level and figure out all the internal forces and reaction forces. So it's quite a lengthy calculations. So I get into component level. So here, minus clockwise. Here, minus clockwise. Positive counterclockwise. Negative clockwise. And this is dB is counterclockwise, and this is counterclockwise. All right, so it goes like that. That's the component end moments that are obtained from moment distributions. And then get in, obtain the shear force. All right. So of course, you can follow through, calculate everything out, no problem. You should be able to do that. Sorry, there's a loading here. All right, so let me just put it down here. So this is 11.9, and this is 11.8. And the shear force is 5.1 there and 7.1 here. All right, so how much is the force there? Global equilibrium tells you that 5.1 that way, 7.1 this way. Summation Fx tells you that you should have a force of 2 there in order to achieve global equilibriums. So that tells you that if I have a roller support there, the force developed at the roller support is a force pulling the frames that way, magnitude of 2 kilonewton. Okay, so this is where we are. We finished the first analysis. Now we need to calculate, because the force is not supposed to be there, so we need to try to cancel that force. So we need to do the second analysis. So maybe I do it here. Everybody have this. So this is the first step. I finished. Now goes to the second step. So second step is I need to apply a force of 2. Any questions about the first part? All right, so I need to calculate this case now. But instead of directly calculating that, which is difficult by moment distributions, because I know that it's going to be pushed that way, the translation is unknown. So what I'm going to do is I'm going to assume, instead of do that, I do this. I'm going to assume this and get that. And then between them, it's just a matter of scaling. Okay, so how much should I assume? It's arbitrary. It's arbitrary because I'm going to arbitrarily assume a delta and then scale it back. This is A, C, D, and B. So because of the translations, component CA is going to have a rigid body rotation. Component DB is going to have a rigid body rotation. So that's the tricky part. So I'm going to see rigid body rotation for AC, which is counterclockwise, and it's delta over 7, length of CA. And then I'm going to see a rigid body rotation angle for BD. Again, is counterclockwise, is delta over 5. So just following the concept of the previous example, you have a settlement. So the starting point is you assume claim condition and let it move. Claim. So claim conditions and let it move delta. So the fixed end moment can be calculated using slope deflection equation just like before, the previous example. So I will be able to calculate the fixed end moment for this component and that component so that I can start my process. So this fixed end moment is 2EI over L. And assume rotations are claimed. So minus 3, 5 AC. So if you substitute that into it, this gives you minus 6 EI 49 delta. I still keep delta open because I know that delta can be arbitrary. It doesn't really matter. What I'm going to do is I'm going to obtain anything arbitrarily and then scale it back to that case. All right. So that's fixed end moment AC. And also fixed end moment CA is exactly the same. So similarly, fixed end moment for BD and DB they are the same. It's 2EI over L. 2EI over L is 5 minus 3 times rigid body rotation angle. So substitute should be minus 6 EI 25 delta. All right, as I can arbitrarily assume delta, any delta will do. So let me set this value to be minus 100, just arbitrarily, right? You can assume minus 200, 300, or 1 million. Doesn't really matter. So I arbitrarily set minus 100. And they are related through some sort of scale. Now, this number actually determines how big delta should be. And delta should be plugged in here. So proportionally, this value should be minus 196. OK? Again, these are very, very arbitrary. It doesn't really matter because the solution is going to scale back to 2 anyway. All right, so with that, then we can execute our second moment distributions. So the second moment distributions goes like this. Okay, so start with the fixed moment. So there, minus 100, minus 100, minus 196, minus 196. All right, so highlight which one is assumed. We assume claimed in order to get the fixed moments. These are originally claimed. So A and B, they are not assumed conditions. A and B are not assumed conditions, but C and D, they are assumed conditions. So then you need to do a balance and distribute on the assumed conditions. So this becomes 50, 50, and then this split. Right? Carry over here, 25. From here to here, 25. In here, 41.1 or 41.2. And here to here is 56.8. So is there any assumed condition? Yes, here are the assumed conditions. So you need to do a balance and distribute, followed by carryover. So you need to do a balance and distribute, carryover a few more times. All right, so that's it. You do a few more time, and when the number gets small, then you can stop. All right. You can go home and then verify those. They're supposed to be the same, maybe due to some sort of numerical errors. All right, so now we finish the second moment distribution analysis. So you then do the same thing like here. Just rework everything here, and then find out how much force is corresponding to produce this kind of deformations. Repeat the bottom, and then you'll be able to obtain this Q value. So let me just do this, fill in the blank. All right, just do component analysis. Get the shear force just like here. Component analysis, get the shear force, and then go to the global value, global conditions. Use the global equilibriums to find the force. And the force is found to be 68.9. So what happened is you take all the results that you obtain here. Now you know Q is 68.9, but we only need to have 2. So whatever you obtain here, you multiply by a scaling factor of 2 over 68.9. That's a scaling factor. And then convert all the results to these conditions. All right, so the results, the final results will be the superpositions of the first analysis and the second analysis. So the moment will be this plus this after you have properly scaled the moment. So let me just give you the final numbers so that you can go home and verify yourself. Is it okay? Yes? Come again, come again. Can I? Yeah. Yeah, right. Everything here, no, all the results you obtain here has to be scaled by this factor. Because this results corresponding to Q equal to 68.9. But we only need to have 2. So you need to take everything and scale by this factor. Yes?
Could you kind of explain again how can you get the minus 100 and minus 190?
As I say, assumed. You assume delta. You can assume anything on delta.
So we assume 1 or something.
Yeah, you can assume 1, you can assume 2, but there's an EI value there, right? So what I did is I take the whole thing and assume it to be minus 100. Because delta is arbitrary. Because different delta will be corresponding to different Q anyway. But you can always come back, scale it properly to get it this. So it doesn't matter how much you assume delta. All right? So it's kind of using a superpositions concept to resolve this issue. So it's not a very straightforward calculations. You have to do a few twists. So I give you the final answer so you can go home and verify that. Again, the final answer will be this. This set of values superimposed with this set of value multiply a factor of that. So please verify yourself. I give you the final answer. All right. That's the final answer for the end moment of the components. And of course, you can certainly also obtain the shear force. All the shear forces follow some local component equilibrium calculations. Yep. That's right. Assume delta. Assume delta. All the moment here is based on this assumed delta. So what is delta value? Is this equal to minus 100? So you can calculate delta value actually. But as I say, this doesn't really matter because delta can be any arbitrary number because I'm going to scale it back to this number anyway, so it really doesn't matter. So what I'm saying is you can assume this to be minus 200, minus 300, minus a million, minus a billion, doesn't really matter. All right, so this is the final example I want to share with you on the moment distribution. All right, any questions about this? So what happened if I assume this to be minus 200? Can you guess what happened if this is minus 200? Hello? Anybody know? If I assume this to be minus 200, what happened? Then everything here will be double, right? This value will be double. So the scale factor will be changed. So this is double, and scale factor is like half. So they multiply, go back exactly the same. So that just shows you that it doesn't really matter how you assume delta. All right, can I leave this example now? Okay, any further questions? All right, unless you have more examples, more questions, otherwise I'll go to let me just briefly touch upon this one. You'll realize that as we goes on, the new methods that I'm going to show you actually make the old methods kind of silly. So we have spent so much effort, and of course, eventually you go to a company and you'll be asked to do a finite element analysis, matrix analysis, and which is far more powerful than everything that we have done here. So let me just give you a glance of that. Okay, this corresponding to chapter 13. No. Yeah, it's coming up. Okay. So I'm going to give you only a few minutes of introductions and see how we change, why we change from hand calculations to computer-based calculations. And you can see the advantage very quickly. But everything starts from slope deflection relationship. It's a starting point, but it's not the only starting point. This is only one trigger point that people make connection to when the computers start to get into our life in the last century, middle of the last century. So this is the slope deflection equations everybody should remember by now. So it's actually telling you the relationship between loading end moments as well as deformations, right? So now, if I redefine everything, I just instead of moving downward, I let it move upward like that. Everything remains the same. So the equation should be the same, right? Rotation angle, rigid body rotation, end moments, loading. So everything should be the same. So they should follow the same set of equations. But instead of not defining deformations explicitly, let's define deformations on top of rotation angles. So this is deformations of point A. This is deformations of point B. And as a result of that, I can write the rigid body rotation angle as a function of displacement delta B and delta A. So this is a relative displacement between A and B. So that's delta. And then delta divided by L is a rigid body rotation angle. Right? So you can rewrite the equations like that. Let's temporarily forget about loading first. Loading needs separate treatment. Right? Loading needs separate treatment. All right, so I am expressing the rigid body rotation angle as a function of displacement now explicitly. Also, I can find out the shear force, VAB and VBA. So I can go into the component level, perform component equilibriums. So for instance, if I want to find VBA, I just come over here, do moment equilibriums, I can find VBA. If I want to find VAB, I just come here, do a moment equilibriums, I find VAB. So VAB and VBA, they are expressed in these two formula. So you take these two formula, plug them in here, then you know that VAB and VBA will be able to be expressed in terms of rotation angle and displacement. So this is the final result here. It becomes a matrix. All right, don't be afraid. Now, if you understand what it means, you'll be so happy, or you'll kind of regret that you didn't know this earlier. So on the left-hand side, what I did here is I just put all four together on the left-hand side in the matrix form. And the right-hand side, I pull out the unknown, or the deformations. So here are the shear force, bending moment, shear force, bending moment. So this is the reaction forces at point A. These are the reaction forces at point B. Here, they are the deformations at point A, deformation at point B. So this is displacement, the rotation angle, displacement, rotation angle. And these two sets of relationships, or these two sets of parameters, they are related through a matrix like that. So this is a very, very nice expression to link directly deformations with internal forces. A very nice expression. A very important expression as well. All right, so let me show you how it works. So let's say that I want to use this set of equations to analyze this example. This is 1 degree or 2 degrees indeterminate structures, depends on how you look at it. So, all right, you analyze the structures. So you can remember that how many methods I have shown you, and they all require very detailed calculations, right? Compatibility, least work principle, or what else? Slope deflections, right? Moment distributions. So they all require some sort of detailed calculations, all right? So what happens if I want to use this? So this is what happened. So just put down everything here. This is point A, this is point B, point A, point B. So point A, displacement equal to 0, rotation angle equal to 0. Point B, displacement equal to 0, rotation not equal to 0. So all three of them equal to 0 except 1. So it tells you this. All three columns there. No contributions. So you only have the last columns contribute to these forces. So if I apply a moment there at B, so that moment should be here, right? So we only have one equation come up. Beautiful, isn't it? Can you see the power of this matrix now? So you can find theta B very quickly using that equations. After you find that, you just multiply correspondingly, and you find shear force, bending moment, shear force. So powerful, isn't it? That's it. You can calculate that very, very quickly. Right, it's beautiful. Okay, so what happens if I have something like this? So you're asked to find displacement, rotation angle at B. So now you remember I have virtual principle, I have Castigliano theories, I have what? Conjugate beams, yeah. So I have direct integrations. I have so many ways to do it, right? But let's see. If I want to do it using this approach, very quickly, it just impose boundary conditions. It just impose boundary conditions. So these two rows, these two columns are no needed. And look at the loading. At the point B, there's a vertical force, no bending moment. So here, at point B, loading, but no bending moment. So eventually, you're solving these equations, these simultaneous equations. So according to this, you're calculating this corner only. So there. So all you need to do is do a matrix inversions. So you just invert this matrix. Oh, sorry, there's an equal sign there. There's an equal sign there. So you just invert this matrix to the other side, and then you'll be able to calculate displacement and rotation angle simultaneously. Of course, after you get that, you just substitute backward, and then you have all the forces. Isn't that very nice to know? All right, so this is actually the beginning of the so-called finite element methods, matrix analysis. So if you want to know more, you should take one more course in your last year. So these are the modern analysis techniques that people use in the company now. So these finite methods become very, very powerful. You can use them to analyze all kinds of structures. So if you want to find out more, no, I don't teach these courses. Of course, you need to survive this course first. All right, so everything comes to an end. You don't want to loop yourself in this course, right? Hopefully you can loop out and then pass this course. So I'm just give you a very quick review on this course, what we have covered and what you're supposed to know. And the final exam will be a comprehensive one. So you will include everything that I have taught, everything, or include something that I have not taught. I just want to I just want to make sure that you're still awake. All right. All right. So what have you got? What have you got? So hopefully by now you should know how to analyze structures under external effects. The external effects include loading, of course, predominantly loading. You should be able to analyze the structure behavior under temperature change, under what? Settlements, misfit, everything. They are classified as external effect. So this is where the structure analysis lie. So after the load estimations, we do structure analysis and then back check to see the serviceability. But we cover this part without covering the structure design, which is supposed to be coming up. So structure analysis, process sort of design, and making sure that you can complete this process. All right, so that's what I say. By now, I hope that you have necessary concepts to analyze structure behavior under external factor. And the structure should include determinate and indeterminate structure. So I want you to have this ability before you pass this course, of course. Analyze the performance of structure system under loads or other external effects. Comprehend and present the structure analysis results, which means like shear force bending moment diagrams, deformation shapes. And of course, these will help you to learn the design issue better, which will be coming up in your next semester. And conducting lab tests, I hope that we have the lab, but I don't know how far did you go there, but this is my wish. So all of these have been covered. All of these have been covered. This is determinate structure analysis. The key there are inference line, applications, deflections, calculations. Equilibrium is running throughout the course, of course. And when you get into indeterminate structure analysis, these are the things that we have covered. So determinate structure analysis. So inference line, still remember? Definitions, graphical approach, Muller-Bruce law principle. And how do we utilize the inference line to estimate the maximum conditions? Cool? Are these material coming back to you now? No? That's good. You still have about 3 weeks to get it back. All right. Deformations. These are applicable to determinate structures, direct integrations, moment areas, conjugate beams, energy principles. Energy principle, we have two energy principles. One is the virtual work principle, and then Castigliano theory. All right? That's a very good review, huh? Direct integrations, moment area, conjugate beams. All right, energy principles. Hey, this is a very nice summary for you. Castigliano theories, and applications of virtual principle is Betty's law. So what is Betty's law? All right. So that is probably one half of the course, and the second half of the course is on indeterminate structure analysis. So first we introduce some approximations. So mainly the approximations center around the use assumptions of inflation points. So depends on whether the loadings are vertical or horizontal. We have different methods, Porter methods, cantilever methods. So, by the time you go to the exam, final exam, you need to have this ability. Just know the name, and you know what it is, right? Porter methods, you say, oh, okay, I know. All right. Cantilever methods, I know. All right. So that's what you need to do. Yeah, I know I'm going to die. All right. All right, so force method. Force methods, the first force methods we introduce is compatibility. Compatibility. And then energy principle. Eventually, we combined. We illustrate that least work principle and Castigliano theories, they can coexist side by side. Right? So I illustrate to you that they can coexist side by side. Sometimes is least work principle, sometimes is Castigliano theories. The issue is whether those forces, they can do any work or not in the virtual work domain. And this very, very important equations that ran through the last two chapters, slope deflection equation, definitions, and just reminding you, but I think that most of people here, you probably know, this only applies to those people who are not here. The notations, let me remind you, the notation I use is different from the notation in the textbook. So if you put down the notations from the textbook, then I will know that you are not in the class most of the time. Does that make sense to you? No, it doesn't make sense. But of course, that should not have any effect on your score. I'm looking at the accuracy, the correctness of your solutions, whether you're following one set of notation or the other set of notation. I don't think it matters too much. And the moment I will ask you to plot at the tensile side, so there should be no ambiguity. So the moment should be plotted at the tensile side. So it doesn't matter how you calculate, how you define your notations. Solution is unique, so they should have the same moment distributions, moment diagrams. All right, that makes sense. So in my own notation, I assume that everything's positive. If they are counterclockwise, and negative if they are clockwise. But that only helped me to calculate. So when you go back to the plotting or the moment diagram, you still need to follow, or shear force diagrams, you still need to follow the definitions. And the last chapters we cover is the moment distribution methods. And I started that methods using two very simple conditions and illustrate to you that it boils down to the calculations of distribution factor, distribution factors. All right, so procedure is fixed end moment, balance distribute, carryover, etc., etc. All right, so what else? So I hope that this is the roadmap of this course. I hope that you have learned all of these in this course. All right, so this is where you are. Hopefully you can successfully pass this course. Question mark. Question mark. But if you have successfully passed this course, the next course for you is concrete design. If you cannot, I'm sorry, pass this course, then you'll be looping here, taking another time. And after the concrete design, there's another course called steel design, which is not a required course. It becomes an optional course. Steel design, I think, is very important as well if you want to climb yourself a structural engineer. All right, so as I say that, we have another course. This is forward-looking, all right, assuming that you have passed. Now, there's another course I introduced just now. It's computer-based matrix analysis, which bring you closer to what the engineers are using now in the company. So if you are interested in the structural analysis, you should go and take that course. Now, in the advanced level, in the PG level, I'm just telling you what you should be expecting. Eventually, you go out, you become a structural engineer. Structural engineer not only need to analyze, but also need to design. But you always designed, in Hong Kong, you design against wind or design against some loading. So you need to also equip yourself if you want to be a very successful, a very capable structural engineer. You need to be able to design tall buildings, design bridge, and consider wind effects or even earthquake effect. All right. Now, so this is by the time you graduate from this program, so these are advanced level. But I wanted to highlight this course. This used to be taught by me. Starting not in this semester, no. I used to cover this course as well. This is called Structural Dynamics or Introduction to Structural Dynamics. Now, everything you learn and we have done here so far, assuming static conditions, but you know in reality it's not static. It's noise. It's dynamic. So wind, like typhoon, earthquake, they are dynamic. They are time functions. So your displacement should be also time functions, right? So in order to analyze structure behavior in the time domain, you need to take this course called Introductions to Structural Dynamics. And with that, then you will be able to learn these courses much better, much better. So I'm suggesting to you, like, if you can, take that course. That is a very, very useful course, which will definitely broaden your vision. Okay. So imagine that are you able to calculate or analyze or even design these buildings? Now, civil engineering is not very traditional anymore. So this is Type A 101. And inside this Type A 101, there's a big mass which is moving inside the building. Next time, if you have a chance to go to Taipei, you should pay a little bit tickets and then go to the top of the building there and take a look at this big steel mass which is moving inside the building. Yeah, so we are not classical, traditional anymore. These kind of device is called tube mass damper. So the buildings are not simply just building anymore. They sometimes equipped with some sort of machines of devices to help the building to make sure the building is safe. So these kind of devices have been very popular now. So like this base isolations. All right. So if you just stay in the classical domain, do analysis, design, I don't think you know what is going on in the world. So this base isolations. So this kind of technology has been used in the earthquake-prone area. So very nice to look at, huh? So like Songkhla Bridge has been built. They are equipped with a system called Structure Health Monitoring System. Structure Health Monitoring Systems. So we are not only doing structure analysis now. Structure analysis is kind of well-established knowledge. So we are doing some more new innovations in the structural domain. So we are interacting with sensor, with equipment, with even smartphones to try to help protect our structure. All right. So structural engineers is not only about structure engineer. So our vision is this. We want to have buildings like that, which is like very powerful and then very, very safe, and then can react to any threat from the ground, from the wind, from the airplane, if there's an airplane hit, right? We want to be able to protect the structures under any circumstances. All right, so. You are you are happy because it's a very good contrast, right? Okay, that's the end of the course. Thank you very much. I wish all you the best in the final exam and move on. All right? All right. Don't see you next year. I don't want to see you.